Okay, welcome everybody. I will do the introduction for Mpofana because Musa can't be here right now. And it's a delight to see so many people in the audience. Thank you guys very much for coming along and joining us in person for the Geotalk. Mpofana is one of our students that's been here. When did you do Onyx? 2018? Okay, so he's been here for a little while. And he's been through the COVID years, and he's finishing up his PhD now. And he's got 2 papers already published, one in geophysics and one in geophysical prospecting. So please let this be some inspiration to you. And his current work that he's going to be presenting today will be on his 3rd paper from his PhD, and he hasn't even submitted it yet. So congratulations, Mpofana. So he's working with Musa Manzi, as most of you know, but he unfortunately isn't here right now, but he assures me he's joining online. And over to you. Thank you so much.
Good evening, everyone. My name is Mpofana Sihoyiya, as Professor has mentioned. I'm doing a PhD in geophysics under the supervision of Professor Musa Manzi. And today I'll be sharing the work we did reprocessing legacy reflecting seismic data for mineral exploration in the Wits Basin and the Bushel Complex. Now, the following is the outline of my presentation. I'll be doing a little bit of touch up on legacy data and the reflection seismic method itself, and some migration, and I'll take you through some results we got from the Wits Basin and the Bushel Complex. Now, as many of you might already know this, the reflection seismic method has its origins in the soft rock environment for oil and gas exploration offshore. It wasn't until the 1980s it was applied in hard rock environment for mineral exploration. And believe it or not, the very first reflection seismic method in hard rock environment were conducted here in South Africa and Canada. So much so that the very first 3D reflection seismic survey for mineral exploration in hard rock environment was conducted in the Wits Basin. So subsequently, that led to South Africa having a huge volume of legacy database from the 1980s and the 1990s. Now, continuously revisiting this legacy data for reprocessing is actually worthwhile, especially for research purposes where you can use it to test new algorithms for reflection seismic processing. And also you can use it to image the subsurface for mineral exploration. Now, legacy data generally refers to those data sets that were collected in the past. And their advantages are that they cover regions that might now not be accessible today because of maybe new environmental laws, even change of ownership of the land, even the development of infrastructure like the highways in some regions. And this data set have an advantage because they were collected in some regions before any mining activity, and they're not contaminated by noise from mining activity, even mining infrastructure. And it is generally cost effective to reprocess legacy data as opposed to going back and recollecting a new data set. Now, there are some challenges dealing with legacy data, including the fact that most of these data sets are stored in outdated formats, and you have to recover them from outdated drives. And most of these data sets, sometimes you find that they're missing coordinates, which makes setting up geometry a nightmare. And in unfortunate situations, you just don't have access to a raw data set to even work on. But there are uses for the information you get out of this data set, because you can use it for mine planning, mine design, mineral exploration. And these results, they can also be used to do quality control, especially when acquiring new data set. You can actually set appropriate acquisition parameters based on the information of the subsurface you got from reprocessing legacy data. Now, the reflection seismic method itself images the subsurface by actually generating small, but you generate a wave field on surface which propagate through the subsurface lithologies, And depending on the physical properties of these lithologies, this wave field can either be refracted, reflected, or diffracted. Now, in the case of reflected waves, it requires significant acoustic impedance contrast between adjacent lithologies. That is to say, there should be a significant difference between the product of velocity and density of the neighboring layers. Now, it's unfortunate that most target horizons that host mineralization usually have thicknesses that are way below the seismic resolution limit of these data set. And sometimes they don't necessarily have significant acoustic impedance contrast with the host rock. So in most situations, we constrain the geometry of these seismically transparent layers by actually imaging the reflections from the hanging wall and the footwall rocks to actually constrain the geometry of these layers. And now this is an example of recorded traces for a wave field that propagated this example of subsurface lithologies. It's now, because we're already imaging these reflections or these horizons that hold mineralization using proxy reflections, we would like to get a subsurface image that resembles the true geology of the subsurface as accurate as possible. Now, ambiguities arise, especially because the geometry of how the reflection seismic data is collected assumes that the recorded wave field for each receiver was reflected directly below that receiver, which, unless you're assuming a horizontally stratified Earth model, we know that is not the case because the wave field can be reflected anywhere in the 3D subsurface space. Now, the migration itself is one of the reflection processing steps, which are very significant because they actually improve the temporal and spatial resolution of a reflection profile. For instance, an unmigrated section is shown here. It would have, especially in complex environment, it would have a lot of diffractions from diffracted waves on edges and things and faults on the subsurface, which would appear, your section now would not appear like the true subsurface. You start having reflections that cross-cut each other, which is not true in the true geology. But what migration does is a step that actually uses the recorded wave field and calculate the true subsurface reflection point of a wave field. And now, hence, creating a much more realistic section of the subsurface, which can be used, it can be interpreted to actually constrain the geometry of the mineralization. Now, this is an example of a migrated section. As you can see, migration has collapsed a lot of these diffractions. And also it actually moves dipping reflections to their true subsurface position. Now, migration can either be applied in time or depth domain, or it can be applied pre or post-step. Now, most of the legacy data that we have collected, because when the reflection seismic method was being applied in the 1980s in hard rock environment, not a lot about the hard rock environment was known, especially in relation to the reflection seismic method. So they would apply migration techniques directly that they used to apply on soft rock environment. And the problem with post-step time migration is that it is very sensitive to lateral velocity variation and structural complexity, which we know that is what actually dominates most of the hard rock environment, especially the Wits Basin and the Bushel Complex. Now, by merely applying pre-stack depth migration technique on this legacy data, you can see a huge improvement on the resultant section. Now, in the Wits Basin, we reprocessed a line near Princeton Mine in order to actually image the Kimberley Reef, the gold-bearing ore of Kimberley Reef, and the geological structures cross-cutting it. And now, it is known that the Kimberley Reef is a composite reef with thicknesses that fall below the seismic resolution limit of this particular legacy profile. And now we actually used these reflections that span it, which is the hanging wall and foot wall, to actually constrain its geometry, and you can find its dip, and you can find its extent, and you can find the strike. And now we envision that the results from this study would actually help enhance the resource evaluation and mine planning and design at Princeton Mine. Now, for those of you that probably know this, Princeton Mine is a relatively new mine that started exploration in the Wits Basin, in the Southern Goldfield specifically, under Great Basin Gold in 2010. And it was quickly put under care 2 years later because they were extracting increasing volumes of mine waste because they were encountering more geological structures than they expected. Now, this mine was bought by Sibanye Stillwater in 2014, and they are currently evaluating the possibility of actually exploiting the Kimberley Reef at depth in this region. Now, this is an example of the geological map of the Southern Goldfield. It is in the town of Balfour. And the reflection seismic profile was collected south of Princeton Mine, as shown by this red line. And there are some mines in the region that used to actually exploit the Kimberley Reef in the past, like the Hex Rivier mine and the old Rutherford Kildare mine. And all these mines were closed around the 1970s. Now the target ore body, which is the Kimberley Reef, UK9A, forms part of the Kimberley Formation of the Taffontein subgroup. And it overlies the Poison shales, these fluoritoid shale markers, which are the footwall of this reef. And we use the reflections from these shales because they have high reflectivity. And we use this to constrain the geometry of the Kimberley Reef. And we also constrain the geometry using the contact between the Fenderstop metabasalts and the Wits Basin, the central rain contact. Now the following are the survey parameters of the profile that was collected in 1993 using a 2D crooked line geometry. It's an 18-kilometer long line traversed from northeast to southwest, collected at 50 meters source spacing and 50 meters receiver spacing. In order to calculate the source of reflectivity along the profile, we actually did 2D acoustic finite difference modeling using a geological model created by Anthropos in 1983 along the profile. And these are the physical properties we use for this rock, the densities and the velocities. All these were taken from previous studies done in the Wits Basin of the physical properties of the rocks. Now, the resultant shot gather from numerical modeling actually shows that we can find reflectivity from the Poison shales, which are shown by the R2 reflection, and the contact between the Fenderstop and the central rain quartzite, which is shown by R1 reflection. And we know from the knowledge of the ore body that it sits directly on top of the Poison shales. Now, the data was a fairly good data set because you can see clear face breaks on the raw shot gather. And the blue shaded area here shows this successfully attenuated surface waves during processing. And this is a processed shot gather showing the continuity of these target reflections. Now, the following is the processing workflow that we followed to process this data set. We actually contrasting the pre-stack time migration and pre-stack depth migration using the Kirchhoff migration algorithm. And the following are the processing parameters. Now, if we are to take the legacy stack that was processed in 1993 and you compare it with the reprocessed stack, you can clearly see there's a lot of reflections that were missed by the 1993 stack. I mean, everything that's near surface is not imaged on this legacy stack. And if we were to use the legacy stack to actually look for the Kimberley Reef, we were going to constrain it to this section of the profile, because we're going to assume that there's no reflections that are associated with the reef on the southern part. But improving this legacy stack actually shows that these Kimberley shales that are associated with, these poison shales that are actually associated with the Kimberley Reef extend all the way to the southern half of the profile. And you can clearly see that the contact between the Karoo and the Fenderstop was missed by the legacy stack. And this critical reflection, which we use as a proxy to constrain the geometry, which is the contact between the Fenderstop and the Wits, was also missed by the legacy stack. So much so it also missed the dolerite intrusion, which is the sill that actually complicates mining. So now if you go mine there using information from this only, you wouldn't actually be aware that there's a dolerite sill there that would actually complicate mining. Now, contrasting Kirchhoff-Pistek time migration and Kirchhoff-Pistek depth migration, the main difference between these two procedures, apart from the fact that one is evaluated in time domain and the other one is evaluated in depth domain, is the fact that is how they treat the velocity model of the subsurface. Because the Kirchhoff-Pistek depth migration honors the lateral velocity variations on the subsurface as opposed to the Kirchhoff-Pistek time, making it more suited for hard rock environment, where we know that there's presence of intrusions of high velocities that is built into low velocity rocks that might actually make the variation of velocity in this lateral direction. Now we can actually clearly see that there's a much more coherency in this reflection, which is the contact between the Karoo and the Fenderstop on a Pistek depth migrated section as compared to the time migrated section. Looking at the velocity model overlaying on the pre-SDM section, because when they were processing the data in the past, I would imagine they went with the concept that velocities increase with depth. But the knowledge we have on the Wits Basin now, the presence of Fenderstop lavas on top of the Wits quartzites, we know that the Fenderstop lavas have higher velocities than the Wits quartzite, even though they overlie the Wits quartzite. So now, by merely inputting higher velocities in this region, we saw a significant improvement on the actually migrated section. So it shows that also experience in the hard rock environment is a lot now, especially in the Wits Basin, as compared to back when it was just the very first reflection seismic survey being conducted. And this is an interpreted section showing some of the interpreted structures that cross-cut the reef. And these were interpreted using the hanging wall reflections and the footwall reflections. Now, in conclusion, we can say that applying new processing algorithms on legacy data, we can see a significant improvement on the stack sections. And we see improved imaging of the subsurface. And we can also give credit to the information we got about the physical properties of the subsurface, because that's where we actually inferred the velocities and densities of the subsurface. That provided also a lot of improvement. And we clearly imaged the proxy reflections that we can use to actually constrain the strike and dip of the UK9 reef. And we envision that this information, because it was published on near surface journal, can actually help with the source evaluation at Princeton Mine. Now, looking at the Bushel Complex. In the Bushel Complex, we're looking at a profile that was collected in the southwestern Bushveld, looking to image the platinum group element mineralization and the geological structures in that region. And here, another fascinating thing is we were applying a newly developed migration technique, which is called the coherency-based Fresnel volume migration. And we trying to look also in the tectonics or tectonic evolution of that region, and look if we can have some input also on the connectivity of the eastern and western bushel. Now the study area is as shown by this rectangle. It's north of Pretoria, and this region has not attracted a lot of geophysical or geological studies because of the thinning of the critical zone which hosts the mineralization in this region. Now, the line traversing from south to north, it cross-cuts some of the major geological structures in the area, like the Chanyan structure, which is a fault associated with the dike, and the Crocodile River fault, which is actually mapped by aeromagnetic data here, this is a Chanyan structure, and here is a signature that correlates to the Crocodile River fault. Now, these are the survey parameters. The line was collected in 1986. It's 50 kilometers in length. It was collected with a source spacing of 50 meters and a silver spacing of 25 meters. Looking at the data, we can see it's a fairly good data set with clear phase breaks, and the shaded area shows the successfully attenuated surface waves during processing. And we can see some continuity of these reflections on reprocessed state, and you can see some improvement. Now, we applied non-conventional processing workflow in this data set because we're applying a new migration technique. We first went with the conventional processing technique just to see if the stack section from conventional and compare it with actually the newly developed stack section from migration. We also did first arrival travel time tomography to actually characterize the velocities of the very near surface lithologies. And we applied the conventional Kirchhoff pre-stack depth migration in the dataset and the coherency-based Fresnel volume migration. Now, this is the first arrival travel time tomography showing the velocities of the very near surface lithologies, and this low velocity region here, we correlated to the Karoo sediments. And I mean, there's faulting also in this region, which is interpreted to correlate with the fault structures that cross-cut the lithologies in this region. And this is the ray path coverage, which is a fairly dense ray path showing good phase breaks. Now, focusing migration techniques like the coherence-based Fresnel volume migration is actually a new migration technique that is based on an extension of a conventional Kirchhoff pre-stack depth migration, which is an integral solution to a wave equation that is represented as a diffraction integral. Now, to demonstrate this, we use a single source and a single diffraction point on subsurface and a single receiver on a homogeneous medium. Now, the wave field, in order to create an image, the recorded wave field energy is actually smeared along the travel time isochron, as shown by the dotted lines. And constructive interference creates an image at diffraction point D, and destructive interference kills noise as well. But the only problem with this is that this technique relies on receivers that actually have a high spatial coverage on surface. Now, in a situation where you don't have a high spatial coverage of your receivers on surface, you get migration artifacts from this technique, which appear as migration smiles on your migrated section. And the coherency migration is actually superior because it does not smear the wave field energy along the travel time isochron, but instead it restricts the diffraction integral by adding an additional weighting factor that is calculated by doing semblance analysis of neighboring receivers, where the semblance coefficients are given 1 for the true diffraction point and 0 elsewhere. And now by so doing, you actually create an image point on the subsurface without actually needing that much of the spatial coverage of the receiver's surface. Now, comparing the legacy post-deck time migrated section with the newly coherency migrated section, the interpretation of the southern half of the section is actually analogous to the interpretation of the coherency migration that we did, with the high frequency, high amplitude reflectivity associated with transverse supergroup, and there's low frequency, low amplitude reflections from D to B are associated with Rustenburg layered suit norites. And these reflections here, which actually appear better on near surface on the legacy stack, are associated with Rustenburg layered suit magnetite. And this seismically transparent region on top here correlates to the Lubbock granites and Rashuk granophyres. Now, the region of interest in this profile is this northern half of the profile. Because on the legacy stack, you can see there are some reflections, but they're not clearly distinguishable. And you can see a general anticlinal structure in this region. And I mean, we're still looking to improve this region because we want to, this low signal to noise ratio region by previous studies, the interpretation that was done on this data set was correlated to out of plane reflectivity in this region. So we're looking to actually do a cross dip move out, and we vary the pseudo 3D velocity model along the profile perpendicular to this region. And actually just do a stack of this section only, just to see how much improvement we can get out of this northern half of the profile. Now, comparing the conventional Kirchhoff pre-stack depth migration, we didn't apply any post-migration processing, but even on both sections. But we can clearly see that the coherency migration outperforms the conventional Kirchhoff pre-stack depth migration, especially on this region of interest. Now, there's some preliminary interpretation of the structures in the region. This is a pseudo 3D view of the profile because it was a crooked line geometry profile. You can actually create a pseudo 3D view of it and create a pseudo 3D volume of velocities around it. And here overlaying is the surface geology. And we can see correlation of some of the major structures that were mapped by geology, like the Crocodile River Fault correlates with that structure we interpreted there, and the Channing structure. Now, this is the velocity model we use to actually migrate this data set. And this region, if you still remember, there was a low velocity region on our travel time tomography model. This low velocity region we added here, we took the velocity information from the travel time. And this is a preliminary interpretation we did. We actually followed the interpretation done by Ojas in the southern half. And in the northern half, we still playing around with it like that. Now, it wasn't until the 1950s, 60s actually, that the emplacement of the Bushel Complex was thought to be through a single lopolith. And the interpretation of the unmigrated profile of this data, because they assume that there are no Bushel Complex rocks available on the northern half of the profile, which subsequently led to them doing a conclusion that the emplacement model of the Bushel Complex is actually a discrete separate cell like a sheet. And an interpretation of a post-deck time migrated section, the one I showed above, by Ojas in 1993, actually concluded that there are some reflections, even though they're not continuous, because already you can see there's an anticlinal structure in this northern region. So, but they concluded that there are some upper zone and main zone rocks in this region, which would actually support that there is some Bushel Complex rocks in the center of the Bushel Complex. And that would actually support the emplacement model of the Bushel Complex as a single major locality. Now, this is a real-time computation of migration. I thought it was cool, and I thought I was going to show this. So, as you can see here, for each receiver, you calculate travel time isochrones, which are the areas that join reflections of equal travel time, like contour lines that are areas that join equal elevations. Isochrones are essentially the same thing. So you can see destructive interference and constructive interference in real time on this video. And some of the structures here, they would appear before they are masked by this high amplitude reflectivity from the transversal reflection. So now we're thinking that maybe on the northern half of this section, to actually improve it, we'll remove these high amplitude reflections from this section. We just only migrate this section to actually be able to characterize this reflectivity on this northern half. And I'd like to thank the following organizations. Thank you.
Great, thank you so much. We'd like to take questions from the audience here. And also for those of you online, please write your questions because we have a problem with our speakers in the room. So please write your questions in the chat and we will get to those. So do we have any questions from the room? Please come up when you come so we can record you on the microphone.
Thanks, Mpofana. That was really cool. Could you maybe just go back 2 slides? I was wondering what's causing that high, I think high amplitude transvaal blob over there. Could you tell us what you think might be causing that in the transvaal?
Also, it would be the high contrast in the physical properties of the rocks of the transvaal, because this seismically or low amplitude, low frequency reflectivity from the bushveld is due to the fact that there's not that much difference in the Rustenburg layer suit densities and velocities rocks. So because the amplitude of reflectivity is actually determined by a reflection coefficient, right, which are calculated by acoustic impedance, which is calculated by density and velocity product. So if you have a high enough or a significant contrast between 2 adjacent lithologies, so if you have, say you have a norite and a gabbro next to each other and they don't vary that much in velocities, you're not going to get that much high amplitude. But if you have maybe a sedimentary rock that is next to igneous rock, then there's a huge contrast in velocity, in both velocities and densities of those 2 rocks. You're expecting high amplitude of reflectivity.
So I guess what I'm getting at is, why is it not continuous?
Oh.
Why the bottom of the section that's so high amplitude, not more to the south?
Oh, here. Oh,
why it's not stratigraphically continuous?
Oh, okay. Also, the acquisition geometry of the profile. So in some regions, as I mentioned, the short spacing was 50 meters. In some regions, they would lower the short spacing, which increases the fold of coverage, right? That would actually improve the amplitude as well.
There's no mineral deposit sitting.
Not that I can tell.
Okay, we got another question in the room. Go ahead.
Just out of curiosity, does that vertical thing happening and what is
Oh,
Just to repeat the question for the people online. The question is about the vertical line at position 50 along the profile.
now the profile was 50 kilometers long, as I mentioned, right? But if you look at this, the actual section is 55 kilometers long, right? Now here is the edge of the profile, right? It could be that the algorithm itself, when it gets to this region, there might be a lot of noise that, because depth migration itself, at the edges, it creates this pseudo reflectivity. Now, it's not advisable to put a lot of interpretation on the edges of your profile, of your seismic profile. It's almost, you create a triangular confidence region on your profile. So you interpret a lot on the edges near surface, but as you go deeper, you narrow it because of the extent of your profile. So,
Any other questions in the room? Go ahead.
So
You have to speak very loudly or come up.
I was curious about how the best way that you read the PSTM with the PSTM.
Yeah.
Now here you just went straight into the PSTM, show you better. Is there any breaking of the PSTM of this complex that we compare?
oh, the question is, why didn't we do a PSTM migration in the Bushel Complex? Now, we learned from previous study. So the study in the West Basin showed that it's the PSTM is actually better than PSTM. So I figured there's no need to actually re-emphasize that in the Bushel Complex. It's inferred from the previous study.
Another question in the room? I've actually got one. In the Wits Basin part, you very briefly mentioned and then glossed over where you implied the reflectivity might correlate with grade. Did I misunderstand that, or you implied mineralization? Okay, could you talk about that?
So basically, because we associate the Kimberley Reef with the poison shale. So we assume that where you find poison shales, you're going to find the Kimberley Reef overlying.
So it doesn't have to do with any thickness or
Of the
variation in the Kimberley Reef.
no, because we can't actually resolve the thickness variation of the Kimberley Reef from this data set. So
Okay, that's good.
One chat question.
And yeah, go ahead and read it.
the question says, nice talk, Mpofana. Question regards slide 29. There is a high energy signal around 55 kilometers, extending over quite a large depth range. Do you think it is geological? If not, what caused it? What can be done to remove it? Or is Prof right? Yeah, I'm assuming, Prof, it's due to the actual formulation of the depth migration. Because I was reading somewhere that as much as depth migration is superior to time migration, because of how it uses interval velocities, at the edges of a velocity model, you would assume the depth migration assumes that the velocity model should be continuous, but now you are at the edges. Sometimes that could actually feed into your depth migration technique and create these linear artifacts on the edges. I mean, to remove it, I would just apply a cutoff in that region. But if I was certain maybe that is geological, then it will actually be worthwhile to look, because actually this video is showing great. It's on that region, but if you look here, there's not much. There is that continuity that appears on each short stack of the isochrones. So if it is geological, it will be better to do a cross dip move out to actually see if is it still as continuous across the dip, because it might be from out of plane reflections also, which is why it doesn't appear as though it's geological feature. So you can play around that. I'm not certain.
So in magnetic data, we often use tapering on the edges. Is that not common in the seismic?
The algorithms themselves, they are designed to actually taper at the edges, because also even the migration, the solution to the wave field, how it's designed is it's supposed to be an integral solution to a continuous wave field to infinity, but you actually take the significant near surface ones and then you taper it using maybe a Hilbert filter, or you can actually transform it to a frequency domain and taper it at the edges. So the migration algorithm itself is designed to have tapering at the edges, but sometimes I guess something's creepy.
Okay, well, I want to thank everybody again. If there's any, oh, there's one more in the chat. Go ahead.
That's just great.
Oh, okay. Okay, any other questions? Let me get one more photograph, and I think, do you have some announcements?
Yeah, just to say it's fantastic to see so many honors students in the room. Well done. Please come again. It's great to see you guys here. And thanks to the whole geophysics team coming too. Please come more often. And thank you, Mpofana. And next week we have Kulakani Kumalo talking about the petrogenesis of the Ventersdorp large igneous province using isotopic constraints. See you next week.